Today we're going to go ahead and solve logs that are a little bit more steps than what we started with. So last time we introduced you guys to solving logs, now we're going to step it up a little bit. We've got log base 5 of 45x minus log base 5 of 3 equals 1. In the last class when we were solving logs, we can convert to an exponential to solve. In this case, you cannot convert to an exponential because there's more than one log. So our first step is going to have to be to get it to a single log so that we can convert it. In order to do that, we have to use those log properties we learned. So the log property tells you that if there is a minus between the two logs and they're both exactly the same base, like these are, then we keep the single log, so log base 5, and we divide our argument. So we would get 45x over 3 is equal to 1. I can go ahead and simplify that to 15x equals 1. Now I'm ready to convert it to an exponential in order to solve. So we drop the base and we switch those and we get 5 to the first power is equal to 15x. We divide by 15 and x is equal to 1/3. You always want to make sure you go back and plug that in to verify that it does not make your argument 0 or negative, since those are undefined. This one does not, so that would be our solution. All right, for our second one here, before I can get started with the properties or with solving, I have to use the properties. And again, they have to be the same log, and this log has a 3 in the front. So I need to use my properties to get rid of that 3. When we have that 3 being multiplied times a log, we know that's the power property that tells us it is the exponent of the argument. So that's the first property I'm going to apply. So I get log base 2 of 8 plus log base 2 of x cubed is equal to 6. Our next property we're going to apply is the product property. And that one tells us if there is a plus in between the two logs, then I keep the log with a base of 2 and we multiply the arguments of 8x cubed. Now we're ready to convert it to an exponential. That part is really important. You've got to be able to convert back and forth. Since our x is in the argument, the only way of freeing this is to convert it to an exponential, because all of this is one unit. This is one number right here. So we drop the 2 and we switch and we get 2 to the 6 is equal to 8x cubed. Now we're left with a cubic here, but we've done that previously in the year, so we're able to do this. And I'm going to use my calculator to simplify here. These two are being multiplied, so I divide by 8. So we get 2 raised to the 6th power. I get out of my exponent and then divided by 8. And so that gives us 8 is equal to x cubed. So earlier in the year, we learned that when there is a cube here, you can do the inverse operation, which is take the cube root. And so we can take the cube root of both sides. The cube root and the x cancel out, and the cube root of 8 is 2. Again, I would want to make sure that I plug that in to verify that it works. All right, number 3 is a property that we haven't quite looked at, but we looked at it as an exponential. We said, for example, that, before we get started there, 3 to the x was equal to 3 to the 5th. We knew that this x was equal to 5 here. Because they both had the same exact base and they were the only thing on each side of the equal sign, the only way to get the same value was if x was 5. We're going to use that same property. If we could get the log base 3 on each side of this equation by itself, then we can set the arguments equal to each other, because that's the way they would have the same value. So my first step is to get rid of this 2 so that they can be the same log, and then put these two together so they could be a single log. So on my left side here, I got log base 3 of x squared. On my right side, they're both the same log, so I'm going to keep the log of base 3, and they're separated by a plus, so I'm going to multiply these arguments. Now I've got the log base 3 on each side of the equal sign. And so in order for them to have the same value, this argument has to be equal to this. So we can set x squared equal to 64. And so now we would take the square root of both sides, and so x would be equal to -8 and +8. Now when we take this -8 and plug it here, it's not going to work because you cannot have a negative argument. So this is an extraneous solution, which means it's a solution to this quadratic, but it is not a solution to our log. So 8 is our only solution. All right, for number 4, again, we've got two things that are separated by a plus here. They're both the same log, so I keep the log base of 3, and then I take x minus 4, and I multiply it times x plus 2. I'm going to go ahead and multiply these out, which means you have to FOIL or use the box, however you multiply those two there. That gives us x squared minus 2x minus 8 is equal to 3. Now I'm ready to convert this to an exponential. So I drop my base and switch. We've got a quadratic. We've done quadratics earlier in the year, so you should be able to do this quadratic. I'm going to go ahead and simplify that. That is 27. When we're solving quadratics, we want to get it set equal to 0. So I'm going to subtract the 27 to get it to the other side. Now we can do factoring. We can do the quadratic formula. We can graph it and find the zeros. You can pick any method you want to solve this quadratic from the quadratic unit. Most of the time it factors, so I'm going to go ahead and factor because I think that's the easiest way. X times x gives me x squared, and then I'm looking for what multiplies to be negative 35 and adds to be negative 2, and that is a negative 7 and a positive 5. What makes this 0 is going to be my solution, so we get 7 because 7 minus 7 is 0, and negative 5 because negative 5 plus 5 is 0. So those are the two solutions. Now remember, you got to take them and plug them back in to verify that they work. When I put in my 7, it works. They are both positive. But when I plug in my negative 5 minus 4 is negative 9 in my argument. We cannot have a negative number in the argument, so that is an extraneous solution. You would not want to put that solution down on your test because that one does not work. I will go ahead and put it in the calculator here so that you can see that the calculator also tells you it does not work. So if we put in our log base here, and I'm going to put in this original equation with that answer. So log base 3, the negative 5 minus 4, and then plus, again, I want to go to my log base, the 3, and then negative 5 plus 2. When I hit enter, it tells me non-real answer. That is not a solution. And it says error if you continue to the next page, so you know this one is not a solution. If we plugged in the 7 there, it would come out to 3, which is my answer there. All right, we've got one more to try here. We've got 2 log x plus 1 equals log of x plus log of x plus 3. So we're going to kind of put all of these together in this one. My first step, I'm going to go ahead and bring this up, the power property. So I get log of x plus 1 squared. Notice that I squared the entire argument because that goes on the entire argument, that exponent in the front right there. So that 2 is the exponent for the entire argument. On the right-hand side, I want to put these two together. They are separated by a plus. So that means that we are going to multiply. Since I have the same exact log on both sides of the equal sign and nothing else, I can go ahead and set my arguments equal to each other. If there was something else on that side, then you could not do that. But since it is just a log on each side and they're both the same log, then you can set the arguments equal to each other. I'm going to go ahead and simplify, so I get x squared plus 2x plus 1 when we FOIL this. You got to use the box or FOIL because that's x plus 1 times x plus 1. On this side, we get x squared plus 3x. When I subtract the x squared, it cancels from both sides. Now I'm going to subtract the 2x to get it to the other side. I get 1 is equal to x. So that is my solution. When I plug it in here, it does not make any of them undefined, so that works. All right, we're going to talk about looking at these equations and knowing what to do. Because at this point, we've solved a lot of different equations. If I got an equation like this is an exponential. I've got two different options in this case because 2 and 32 can have the same base. So I can do common base, or I can convert to a log in order to solve that equation. For the second one, if I have one log on each side of the equation, I can go ahead and set the arguments equal to each other. This one here, 4 to the x equals 32. You can do common base or you can convert to an exponential. That one's a really easy one to convert to an exponential. You drop the 4, so we get log base 4 of 32, so that's an easy one to put in the calculator. For D, we have 2 logs on this side. So the first thing you have to do is use your properties of logs. Use the properties of logs to get a single log. Then you can convert it to an exponential. For E here, we have this value here. You would want to get rid of the 4, so we would take the 4th root of each side. And then this last one, log base 8 of x is equal to 0.3. We're solving for the argument, so you would want to convert that to an exponential. So make sure that before you get started in solving, look at the equation that you have and try and determine what would be the best method to solve it. We're going to look further into applications of exponentials and logs next class period, but I do want to be touching on applications as we go forward. So this says a decibel is a unit used to measure the loudness of sound. The formula for the loudness of a sound is given by this equation, where dB is the decibel level. The quantity I naught is the intensity of the threshold sound, a sound that can be barely perceived. The quantity I is the number of times more intense a sound is than the threshold sound. The sound in a quiet library is about 1,000 times as intense as the threshold sound. I is equal to 1,000 times I naught. Calculate the decibel level. So if our decibel level, dB, was equal to 10 times the log, our I here, they told us, was 1,000 times I naught. Here is our equation. This is the easiest kind of equation they give you because I naught over I naught cancels, and so we get dB is equal to 10 times the log of 1,000. Well, everything's on the right-hand side, so there's the variable that you're looking for, the unknown, is on this side, so all you have to do is plug it into the calculator. Since that's the common log, I could go ahead and use the log button, so I do 10 times the log of 1,000. And so that would be 30 decibels. Part B says the sound of a crying baby registers at 115 decibels. How many times more intense is the sound than the threshold sound? So in this case, they're giving us the decibels, so I'm going to plug that in for my left side of the equation, the dB. Then I get 10 times the log, and I'm looking for how many times, so that's x times I naught over I naught. Because it says how many times more intense. So how many times the intensity of the initial one. This cancels, and so we get 115 equals 10 times the log of x. In order to solve for this log, I need to get rid of this 10. So they're being multiplied, so I divide by 10. Run out of space. So that's 11.5 is equal to log of x. The common log has a base of 10. So when I convert this to an exponential now, that is going to be 10 to the 11.5 is equal to x. So this is 10 to the 11.5 times more intense. Than the threshold sound. All right, here is another one. The Richter scale, which measures the magnitude of an earthquake, follows a logarithmic scale. Because the Richter scale uses a base of 10, each increase of 1 in the strength of an earthquake on the Richter scale means that there is 10 times the intensity. In other words, a 6 earthquake is 10 times as strong as a 5 earthquake. To determine the intensity of an earthquake, which is the amount of ground movement, seismologists use the equation R equals log of I over I naught, where R is the magnitude, I is the intensity, and I naught is a minimum intensity. For this problem, we're going to go ahead and use I naught as 1. The recent earthquake in Haiti had a magnitude of 7.0, while the earthquake in Chile had a magnitude of 8.8. Compare the intensities of the two earthquakes. All right, so we'll start with the Haiti one. And so that one had a Richter scale of 7. So I get 7 log of I over 1. We're using that initial intensity, I naught, as 1. So in order to convert this, I would have to change it to a exponential, because this is what we're solving for right here. So my unknown is in the argument, so I want to change it to an exponential. So I drop my base, which would be 10 for the common log, raise it to the 7th power, is equal to I. So the intensity of the Haiti earthquake was 10 to the 7th power. Now for the Chile one, it had a Richter scale of 8.8. Again, we want to convert this to an exponential, so I drop the base, that is 10 to the 8.8. And so the intensity on that one is 8.8. If we want to compare the two to see how much stronger that Chile one was, we would take that 10 to the 8.8 and divide it by 10 to the 7th. And so we get 10 raised to the 8.8 power. I get out of my exponent and divide by 10 to the 7th power. So it was 63 times as intense. So there's some applications with logs. We'll continue to look at more applications as we move forward. Hopefully you've got a good understanding on how to solve those, and hopefully you're getting really good at changing between exponentials and logs, because that's a great part of the solving.